Welcome, everyone. Today we are going to talk about big data, AI, and digital phenotyping in neuroscience. So, these are really hot topics in the field, and today we are going to go into the hot takes of Garima Gupta, who is the guest today. So, welcome. So, I would like to open the stage by asking that why this conversation matters now more than ever.
So hello everyone. As we everyone that it's becoming almost impossible to talk about neuroscience today without hearing words like big data or AI. Our phones track where we go, wearables track how we sleep and move. Even our digital interactions leave behind a continuous trace of behavior. And yet, despite collecting more behavioral data than ever before, psychiatry still struggles with some very basic questions such as who will respond to treatment, who is at risk of relapse, and how do symptoms actually unfold in life. That tension is what I want to explore in this episode. I'm approaching this not as an expert, but as someone actively building towards this space, trying to understand how big data and AI can genuinely support translational neuroscience without overpromising what they can deliver. So, this episode is less about the hype of big data or AI and careful thinking.
Right. So, how are mobile sensing variables and digital interactions, the data that we are getting, reshaping the measurement of behavior in translational neuroscience?
Ritika, traditionally, the behavioral neuroscience has relied on snapshots, such as a task completed in a lab or a questionnaire filled out once every few months, and also a clinical assessment at a single time point. Those measures are valuable, but behavior, especially in psychiatric conditions, doesn't really work in snapshots. Symptoms fluctuate and they are shaped by sleep, stress, social context, and routine. And often, the most important changes are gradual rather than dramatic. This is where mobile sensing and wearables have started to shift the landscape. Instead of asking someone how they usually feel, we can sometimes just observe patterns such as daily activity rhythms or sleep regularity over weeks in movement or routine or even indirect markers of social engagement. So, in a way, behavior becomes something we track over time, not just something we sample. What I find especially interesting is that much of this data is passive. People don't have to constantly report symptoms. Behavior is inferred from patterns that accumulate naturally. For psychiatric research, this matters because early warning signs are often subtle, such as, for example, a slight disruption in sleep could be an early or a loss of regularity or a gradual withdrawal from specific or typical routine. So this digital phenotyping gives us access to those slow shifts. But here's the important part. More data doesn't automatically mean better understanding. Digital traces are proxies, they don't come with built in meaning. So while the measurement changes, interpretation still depends on theory, context, and careful behaving. In other words, we can say that digital phenotyping doesn't replace clinical insight. It changes when and how we observe behavior.
Right. So let's get into the other things. Like, what are, multimodal integration when we talk about these concepts? Are these somehow more meaningful or matter more than any single signal, or what is your take on that?
That's a very important question to ask. One reason big data has been so appealing in neuroscience is that no single level of analysis tells the whole story. You see, behavior alone is noisy. Brain measures alone can be hard to interpret. And genetics often tells us about vulnerability, not outcome. And what we have learned often the hard way is that no single layer is reliable on its own. That's why the field has increasingly moved towards multimodal integration. The logic is actually quite intuitive. Like behavior gives us fun how someone acts and adapts in the world. Brain data helps us understand underlying circuits, and genetics can inform risk, sensitivity, or long term trajectories. Individually, each of these signals is limited. Together, they can sometimes reveal patterns that are more stable and informative. What stands out to me is that behavior often plays a central role here. It anchors the biology. It gives brain and genetic data something to mean for the person. Without behavior, biological signals can become abstract. Behavior connects them back to lived experiences. And for translational neuroscience, that anchoring is essential. So integration isn't about adding complexity for its own sake. It's about letting different levels of data constrain each other and reduce over interpretation.
Right. So, what are certain compelling examples where machine learning on multimodal data, such as behavioral, imaging, genetics, has uncovered clinically very meaningful subtypes or predictors of treatment response?
So, machine learning tends to attract the most attention when it promises prediction. Predictions such as predicting diagnosis or predicting treatment response or predicting relapse of a disease. And in some cases, this has genuinely worked, especially when models are grounded in well defined behavioral measures. For example, instead of grouping people purely by diagnostic labels, some studies have looked at patterns across behavior and brain data. What emerged weren't neat diagnostic categories, but subgroups where people who looked similar on paper yet differed meaningfully in symptom trajectory or treatment response. That kind of insight matters. But what's striking in this more convincing cases isn't the sophistication of algorithm. It's the care taken with the inputs. For example, several constructs, careful validation, and testing an independent sample. So basically, machine learning works best when it's used to refine understanding. Replace it. We can never replace understanding of that machine learning, but we can refine the understanding. So we can say altogether that AI doesn't discover meaning on its own. It just simplifies or amplifies whatever structure we give it. And when the structure is weak, even very impressive models don't translate.
Right. So, what are the main pitfalls like overfitting, lack of interpretability, data bias, or weak clinical grounding? Can you go into the depths of them?
Yes, sir. So this is where caution becomes important. There are many pitfalls. One of the major risk is overfitting. It's like with large complex data sets, models can learn patterns that look convincing but don't generalize. They perform beautifully until they are tested elsewhere. And another issue is interpretability. Like in clinical settings, prediction alone is rarely enough. Clinicians want to understand why a model makes a recommendation. Patients want explanation they can trust. So, if a model can't be linked back to behavior or biology, its usefulness becomes limited. Then there's data bias. Digital phenotyping depends on access to technology. Smartphones and wearables aren't used the same way across populations. So models can end up reflecting social or economic differences rather than neural or behavioral mechanism. And this is the part that personally concerns the most. What worries me isn't bad models. It's models that look convincing but don't survive contact with real patients. Finally, there's a weak clinical grounding. Sometimes AI is applied simply because the data exists, not because it addresses a meaningful clinical question. In those cases, accuracy matrices may look impressive, but the real world impact remains unclear. So the risk isn't AI itself. We can say it's using powerful tools without enough conceptual depth.
Right. So, what skills in statistics, programming, or data science most differentiate strong PhD application in this space, do you think?
Okay, so as we all know that there's a lot of pressure on students to appear highly technical when talking about AI and big data. But in my opinion, what I have seen, faculty aren't necessarily looking for advanced expertise. They are just looking for trajectory. They just want to see that someone is actively building skills and understands why those skills matter. Uh, Statistical thinking is foundational. Understanding variability, uncertainty, and validation goes further than knowing specific algorithm. And basic programming literacy matters too. You see, being comfortable working with data, even at a modest level, makes collaboration possible. And as we know, that collaboration plays a major role in a PhD or or becoming a successful researcher. Then we can say there's data discipline that knowing how to clean, document, and structure data is surprisingly rare and incredibly valuable. Interestingly, knowing 10 algorithm matters less than understanding why your model might fail. That is the most crucial part of analysis. And finally, conceptual clarity. Being able to say this model answers this question and it cannot answer that one. That ability to reason about scope is often what separates strong applicants from those who want buzzwords. In this space, depth usually matters more than breadth.
Right. Lastly, I would want you to reflect on why big data still needs human judgment.
So, when I think about big data, AI, and digital phenotyping in neuroscience, I don't see them as shortcuts. I see them as amplifiers. They amplify good questions, and they amplify weak ones as well. They amplify careful thinking and contradictory, careless assumptions as well. They give us unprecedented access to behavior in real world settings, but they also demand more responsibility in interpretation. As someone actively building towards this field, what excites me isn't the technology itself. It's the possibility of measuring behavior in ways that are more continuous, conceptual, and human, while staying grounded in theory and clinical relevance. If anything, big data makes one thing very clear: good questions still matters more than powerful tools. And that's the direction I want my PhD training to move in. And thank you everyone for listening.
Yeah, I would also like to extend my thanks for the listeners for listening to us. With that, I wrap up this episode. Thank you.
Thank you.